Recording. All right, and our final talk today is Ziquan Yang from Wisconsin. Talk about algebraic. All right. So let me give a basic setup. Suppose I have a smooth morphism of schemes. Let me call this pi. And suppose I take a vector bundle, well, or even just a partially covariant sheaf with interval connection, which is denoted by MIC in Christian's talk. So, as usual, this nabla is an integral connection. Well, with curvature 0. Then the algebraic Rham cohomology of this object is defined to be the higher direct image of the Rham complex of this vector bundle. So this Rham complex is defined such that it is defined as following. So you send omega tensor with E to d omega tensor with E plus minus 1 to the I omega wedge. Nothing. Okay, so we mostly care about the case when this vector bundle is trivial. So namely, you just take the structure sheaf together with a standard differentiation. And in that case, this is the algebraic Rham cohomology of our morphism. But it'll soon be clear that allowing this a little more flexibility is useful. Here's another point of view on what this object is. So HR per Q, the Rham X is the Q right derived functor of the following functor. So you map from MIC X over S to MIC S over S. And this is really the same thing as partially coherent sheaves from S. And you send your E nabla to the push forward of the horizontal sections. Okay? And to see that this definition agrees with that, you make use of Grothendieck's infinitesimal sign. In calculus AP, you can make use of the crystalline site, although I think technically for this statement, you don't need the full course of physics. All right, so my main goal today is to explain the constructions of three things: Hodge filtration, the conjugate filtration, and Gauss-Manin connection. These are all exercises from the following basic fact from homological algebra. I'll basically do the same thing twice. But here's the basic homological algebra fact. an A, B, and a Deligne category. Let me just write A, B cat with a countable direct sum. Basically, we want this in case we need to form total complex or some double complex, but I won't really talk about that. And enough injectives. Well, this is a standard assumption to do homological algebra. Then suppose now you have a functor between two abelian categories, and K is a filtered complex. So I'm always going to assume that the filtration is decreasing. If you happen to have a complex with ascending filtration, just flip the sign and you get a descending filtration. It's like you never have to consider right actions. Whenever you have a right action, you by taking inverse, you get a left fraction.
K is the filtration of that.
Yes. So, all right.
Wait, I think F is the filtration of K, right?
Ah, yeah, yes. Let me assume that this is finitely filtered. Then there exists a spectral sequence whose E1 page is given by R, P plus Q, F, the P graded pieces, K, convergence to R, P plus Q, F, K. Okay. After I restrict to considering characteristic P things, I'll not use PQ anymore, but let's use PQ now.
So all the F's in this last line are the functor, not the filtration.
Oh, Jesus, yes. Let's say T. Okay, so this is the basic homological algebra that I'm going to use. Oh, sorry, I haven't finished the statement. Moreover, the differential is some very concrete object. The differential goes, well, on the E1 page goes from PQ to E1 P plus 1 Q. And this is just a boundary map. Of RQT of the following short exact sequence. You go from GR P plus 1, K, and then you go to FP mod FP plus 2, then you go to GR P. What?
The E1 page isn't
R. Sorry. Which part am I asking? This. This?
Yeah.
No, yeah. This is PQ, and this is P plus Q. Yeah, it'll be clear later that this indexing is actually correct. Okay. The example is right here. So first, let me construct the Hall filtration.
Just trying to T's here is a left exact function, right?
Ah, yes. So for our purposes, this T is always push forward, which is left exact. Okay, so first let me construct a Hall filtration. So I know Elon has already talked about this. Please bear with me for a little repetition. So In fact, there's a very general definition of hot filtration. Suppose K is any complex in A. Then we can define a stupid filtration, little h for Hodge, just by truncation. So in particular, the Hodge filtration applied to a shift is this. Okay, so now I'm going to apply this to the case when E is just a structure sheaf. So then we obtain a spectral sequence E1 PQ. This is R push forward. Okay, this is P plus Q. GRP of the Rham complex. And this is RP plus Q pi omega P x over S shifted by minus P. Okay? Because when you compute this, you actually land in the degree P term. And this is just a module, so you need to shift by minus P. But now it works out because then this P and this P will cancel out, and you have the usual form of Hodge the Rham special sequence. Okay? And this is what we normally write by HP plus Q the Rham x over x. So recall that to say that you have a certain spectral sequence which converges to something means there exists a filtration on this something whose graded pieces is computed by the E infinity page. So when we write when we write this convergence, it is implied that this object carries a filtration whose graded pieces are the E infinity page. And that filtration is, of course, called the Hodge filtration. All right, so now let me explain the conjugate filtration.
Before you do that,
Yeah.
so it's not an abstract filtration, right? It's like the image of some map.
Yes. I was just too lazy to. Okay. Yeah.
You don't have to say it. You don't
okay.
put it in those words.
Yeah. Yes. I mean, let me write it down anyway. As I said, it's a very concrete. Q, the Rham is the image of RP plus. I use Q, right? Yeah. Okay. So Q push forward F. Did I use? Okay, I use I. Okay, so Fi. Yeah. Okay. All right, so let me introduce a conjugate filtration. What is kind of ironic is that conjugate filtration is defined by a wiser filtration, but its property is not as good as the Hodge filtration. Well, depending on perspective. Okay, so again, let me state some very general thing. That KF be a filtered complex. let me assume that this is finitely filtered again, just to be safe. In A, there is a decollage operation. I'm not sure if I pronounced this correctly. So you can define a new filtration, DEC, where DEC is short for decollage. PKN, this is Z. Z means the kernel of your differentials minus P. So somehow you want to shift your degrees a little bit. Then there is a natural map. U, which goes from the E0 page, P n minus P, DEC K, going to E1 of P plus N minus P K.
Sorry, how does decollage depend on that?
You start with a filtered complex, you define a new filtered complex.
Yeah, but I just don't
that's a great question. It seems I wrote some nonsense.
Sorry, I can never remember.
I can't either.
E1 here refers to kernel differential of the E1.
What? Sorry?
Sorry, so Z1 is presumably it's what you use to construct the special sequence. So probably a subspace of KM, which by differential gets displaced.
Right, okay.
It goes into at least E plus M.
Okay, so I'm saying to make sense of this Z1, you already need to look at the E1 page of your original filtered complex.
What's the construction?
For the identity.
My suggestion is that we don't try to figure out decollage on the board because it would
Sure, of course,
just
yes.
say
Yes.
the output of it. It's unfair.
Okay, so yeah, I just wanted to mention that there is this operation, and now we put on. Okay, so on K, there is some. Okay, what's the name of this? Okay, probably this should be called truncation. This is also some standard way of putting a truncation on the complex. So this is n if n is equal to p, kernel of p, if n is equal to p, and 0 if n is squared. Okay, so this is an increasing ascending filtration. Again, you can obtain a decreasing filtration by switching sign. And we apply decollage to the Rham complex together with this other filtration. And then we obtain E2 PQ goes from RP convergent to the same. All right, So the reason I mentioned this is that it is still using this, which gives you an E1 page, but after you apply decollage, there's a shift of the index of your page, so you end up with an E2 page. And skipped all the intermediate computations, but at least it should convince you why this conjugate filtration is on E2 page as opposed to the E1 page. And
maybe the way to say it,
yeah.
If you're scared of decollage, you can go on Wikipedia and search second hypercohomology spectral sequence.
I Googled that yesterday, and I didn't find a very satisfactory document. And eventually I went to Deligne's, theory, they Hodge, where he defined this, and this is the best reference I found.
Sorry, but also decollage is something that's secretly already been constructed in the construction of spectral sequence. So even the spectral sequence exists.
You mean in the construction of this?
Yeah, you could have just run the construction of your third chord literally for this operation, and then just make the change of coordinates on your EP plate. Okay.
Sorry, you're saying something happened already here, or for the shifting? No.
Well,
here already.
I just mean we could have, you have a filter complex.
Yes.
You could have plugged it into your formula.
Yes.
And you would have gotten some spectral sequence.
Yes.
So it's a collection of pages, but then you just permuted the terms of the spectral sequence, so the differentials now on the page you start with go not horizontally but diagonally. This would be what you did. Okay. Well, you could change it, yeah. So I mean, it's just a
You have to make it to make a special sequence.
Thanks. Where was I? All right. So by this fancy age, I mean, this is a naive cohomology. You have a complex of sheaths, and you just take kernel mod image. So this object is in particular a sheath. Okay. So again, whenever you have a convergent spectral sequence, it implies that there is some filtration on whatever you converge to, and the resulting filtration is called conjugate filtration. All right. So the upshot is that both the Hodge and the conjugate filtration are obtained by applying this simple homological algebra, except that you are putting different filtrations on your Rham complex.
Maybe it's worth mentioning in the resulting filtration, you can write in slowly analogous way the image of some map of homology.
Okay, well, what's a very clean way of
Oh, you don't have to write it, but I mean, Talus from the K board, the subcomplex of K board, and pick the image on.
So it's again?
So I mean, you've written some subcomplexes to K bullets, they map to K bullet. So you can look at the image from a map to RP plus Q, Talus and P, K bullet to RP plus Q. And in this particular example, say that again.
Sorry, constant thinking form of force.
That's all right, that's all right.
All right, so then let me construct the Gauss-Manin connection.
I'm sorry, maybe in this generality what I'm saying is not true. Here is P.
Oh, okay. I'll probably mention that. Yeah, I'll talk about cardiac isomorphism. So suppose now you, we append a new morphism such that both pi and f are smooth. So then there is a Gauss-Manin, canonical Gauss-Manin connection on the relative the Rham cohomology of, okay, actually, let me use, let me write R2 push pi push forward omega x over s. So somehow this connection is denoted with a Chinese character in Ka's paper. I mean, he probably wrote Japanese, but this Japanese character comes from Chinese anyway. Yeah. So I thought about keeping writing this because I can, but since people are taking notes, let me refrain from doing so. All right. So okay. Why should there be such a connection? Whenever you see a factorization of like this, you probably, a natural thing to do is to try to consider a Larrey's spectral sequence. And ideally, you should have something like H upper P, the Rham S over T, and then H upper Q, the Rham X over S, convergent to P plus Q, the Rham X over S.
Does the map have to be proper over here?
No. Just move. But if you write down a Larrey's spectral sequence, you need to have a factorization of functors. And if you consider the source and target categories of your functors, it should go from IMIC of x over s, x over t, and then you restrict to IMIC x over s. So why is this a restriction? These are connections which are OT linear. These are connections which are OS linear, but OS linear is OT linear. And then you map to IMIC T over T, which is again the same as parse-equivalent sheaves on T. So if you believe that there should be such a spectral sequence, then that means this intermediate object you obtain should lie in this intermediate category. So that in particular suggests that you should have a natural connection on this object. And this is precisely the Gauss-Manin connection.
Shouldn't it be an MIC of S over T?
You're right. Sorry. Yeah.
Can I ask you a question?
Yeah.
Yeah, just for your family theories. So for this trivial bundle case, does the spectral sequence generate well?
In calculus 0, yes. In calculus P, it's a theorem of Deligne-Illusie, which tells you a necessary condition for this. And hopefully I'll get to that as well. All right, so here's a more concrete construction of the Gauss-Manin connection. So recall there is a short exact sequence which goes from 0 to pi upper star omega 1 s over t goes to omega x over t equals omega 1 x over s. And then we put the following, we put a filtration on the Rham complex of x over t to be the image of pi star omega I s over t tensor with OX, omega dot minus I x over t mapping to omega x over t. Okay, so we were putting a filtration on the Rham complex of x over t because, as you can imagine, we want to run some spectral sequence to compute this, and the thing we want should be an output of that spectral sequence. So the gridded pieces of this filtration, by virtue of this short exact sequence, looks like this. Okay. So note here. Yeah. So sorry. This is. Okay. So here you are taking image inside the Rham complex of x over t, but in the gridded pieces you see x over s because you're taking the gridded pieces. All right. So
what is this doing? It's like counting how many of the coordinates are pulled back from x.
yes. All right. So then we obtain a corresponding spectral sequence whose E1 page looks as follows. GRP, and this is R P plus Q pi lower star pi upper star omega x. Sorry, this is P s over t tensor with omega dot minus p x over s. And this is isomorphic to by the projection formula. I mean, there is a version of the projection formula which also takes care of derived functors, and you use the fact that this is locally free. Well, finite locally free. So then you get omega p s over t tensor with rq pi lower star omega x over s. So once you apply rp plus q to this term, this minus p will cancel out with this copy of p, so then you're left with a q over here. And this object is, of course, the Rham cohomology of x over s. So in fact, this E1 page, this is nothing but the Rham complex of your Rham cohomology over S plus the Gauss-Manin connection. So in particular, your Gauss-Manin connection is obtained by taking the boundary map of some short exact sequence. Okay, so let me check the time real quick. How long do I have?
Probably until 5:20.
5:20. Oh, okay, good. So more concretely, where were we? Oh yeah. So this D1 is obtained by the boundary map q pi lower star applied to the following short exact sequence. 0 goes from pi upper star omega s over t. Sorry, no, yeah, right. Okay, this is right. Tensor with omega minus 1 x over s to something. This is not important, so let me just write blah. And then you go to omega x over s 0. Yeah. Okay.
Can I try to say why this is like a natural thing to do?
What is a natural thing like this?
This short test.
Yeah, sure.
Yeah. So okay. So what are you trying to do when you do the economic questions? You take cohomology class on a family of cohomology classes on the fibers of pi, and you're trying to differentiate them along the vector field.
Yes.
So if you represent such a thing by like a check hypercocycle for omega to 1 x over s.
Where? Here.
On the right hand side.
This.
Yeah.
Okay.
So how do you write down the boundary map? You take a pre-image in blah.
Mm-hmm.
Well, if you write down what blah actually is,
Okay.
it's like something capturing something on the total space of x.
Mm-hmm.
Then you apply the exterior derivative, right? That's what the differential in blah is.
Mm-hmm.
And then it comes from that thing on the left. So you're literally taking a cohomology on the total space and differentiating it. Like that's,
Right.
Yeah. That's what it's cohomology.
Right. It'll be more apparent. Yeah. So it's a follow remark to what Daniel just said. If you look at Ka's paper, that there is also a very local computation which computes exactly what this boundary map is in terms of local étale coordinates. And yes, there you need to look at what this blah is. For now, let me ignore this. Okay, so the point I want to get to is the following. So if you apply your hot filtration to a star, you obtain this. You have a f minus 1 omega x over s shifted by minus 1, mapping to another blah. And then you go to fi omega x over s. Okay. And then if you compare this sequence to this sequence, and you, what do I want to say? You obtain the following commutative diagram just because some natural property of considering boundary maps in the homological algebra. Okay, so what is the point of writing this down? The point is that this explains Griffith's transversality. If you ask why is that you take something in the fi piece and you have to land in fi minus 1 piece, the reason is that you have this diagram and you factor through this object. And why do we have this f minus 1 coming up? Well, it comes up because there is this shift in your short exact sequence. So essentially, what I want to say is that if you look at the complex analytic explanation for Griffith's transversality, then somewhere you see an explanation saying that, somehow somewhere your anti-holomorphic degree goes up by 1 and your holomorphic degree decreases by 1. And this is a homological algebra explanation of why that happens. All right, so now let me get to characteristic P. All right, I have 20 minutes, so hopefully it's good. So let me get back to the setting when I have x over s, but now let me assume that s is a characteristic P. So then we have the following standard construction. You have your x over s, and then you take the pullback along the absolute Frobenius. And then your pullback is typically denoted by x parenthesis p. And then now you take another copy of x, you map to itself via absolute Frobenius, and this is again pi, and this is pi Frobenius twist. And then by the universal property of pullback, you obtain a morphism from x to it's for Frobenius twist, which is normally written by f x over s. And in the following, I'm going to write the relative Frobenius simply as f. So note, if I do relative Frobenius, push forward the Rham complex, this is O x parenthesis p linear, because dx to the power of p is equal to let me write this. Okay. So now let me state Cartier isomorphism. There exists a unique isomorphism of O x Frobenius twist modules for each natural number that goes from omega I x Frobenius twist going to the cohomology of Frobenius push forward of your Rham complex. Okay. Such that C inverse sends 1 to 1, and C inverse sends omega wedge tau to C inverse omega wedge C inverse tau, and C inverse B sigma inverse x. So where sigma is this morphism from Frobenius twist of x itself. 1, 2, 3. This is the class of x to p minus 1 dx. What? I mean, if you take I to be 0. Yeah. Then you just have a structure sheaf of x twist to OX.
So the
Yes.
This is like the left hand or the right hand?
This.
What does it mean? The
What's inside what?
something inverse
Where?
formula. In the formula,
Yes.
C inverse of P of
C inverse sigma?
sigma.
Yes.
And what is
Sigma is this horizontal. Okay. I have a little space here, so let me complete the statement. The corollary of this is that C induces an iso of OS modules from E to AB. Well, this is the special sequence of your conjugate hot filtration. See, now I'm using AB. It goes from RA, high lower star, HB, omega x over S. Okay. Goes to RA, high lower star, P twist, sigma inverse omega B x over S. Okay. I originally planned to explain why this explain this, but I think I'm short on time, so let me skip this. The main point is that this relative Frobenius morphism is a homomorphism. So in particular, it is exact. Okay. So now let me give a main theorem of Deligne-Illusie. Assume that S lifts to some S tilde flat over Z mod P squared Z. And the Frobenius twist of P lifts to a smooth morphism over S tilde. Then the complex tau less than P, Frobenius push forward of the structure sheaf is decomposable. So more precisely, each lift x p tilde to over S tilde induces a decomposition, i.e. a quasi-isomorphism from the direct sum. Well, this is in fact the complex. Hi, Frobenius push forward x over S, shift by minus I. So you view this as a complex with zero differentials in between. And then you map to Frobenius push forward of the Rham complex. So by quasi-isomorphism is just an isomorph. It's just a morphism which induces isomorphisms on cohomology. And by Cartier isomorphism, the left-hand side can be identified with this. You have omega I x to f twist over s shift by minus I. Okay. I have 10 minutes left. Let me decide what I want to do. Do you prefer that I mention the generation of hot Rham in the event page in capital 0, or I should say something about p-curvature? Oh, okay, all right. So let me just say that as a consequence of this, if you have a smooth proper variety defined over a perfect field of in characteristic P, and you lift to over Z mod PZ or W2 of your K, then if your dimension is strictly less than P, then your hot Rham spectral sequence degenerates. It's some dimension counting argument, which by Daniel's suggestion, I'll skip. And by some spreading out argument, you can show that this implies that hot Rham spectral sequence always degenerates in characteristic 0.
For the degeneration, you need to assume that the fiber is a proper flat.
For the degeneration statement, yes, you want properness, because we want your hot cohomology and your Rham cohomology to all be finite dimensional. So we want property. But I think other than that, we don't need property. All right, let me say something about p-curvature. Okay, so now let me consider S over T. Again, let's assume that this is smooth. And let's take a quasi-Fourier sheaf with integrable connection. Then recall that this nabla is OT linear. But from this nabla, we can define a morphism denoted by psi, which sends, sorry, let's skip ahead. Another way to present the same data is to write a morphism from the space of T derivations. This is the Hom OS from omega 1 S over T to OS. In fact, I like to denote it by the relative tangent bundle, but let me follow what Cos does. And then you map to end of E, which are OT linear. Okay, using this presentation, we can define a psi which goes from S over T to E end OS linear endomorphisms, which sends D to nabla D to the power P minus nabla D to the power P. Ah, yes, of course. Okay, let me read this. Okay, so we have the property that psi GD is equal to G to the P psi D if G is taken from OS and D is a derivation. So this implies that this psi, in fact, also gives me a morphism to the pullback and the absolute provenience on S of omega S over T considered with E. Okay, so this is another way to present the same data, emphasizing that psi D is p-linear in this case. Okay, so I have 5 minutes left. Okay, so here's the main thing that I want to state about p-curvature. So your usual Gauss-Manin connection. Okay, sorry. Now we are back to a relative case. Your usual Gauss-Manin connection will act on the terms of your conjugate spectral sequence. So this is pi, this is, wait, this is, yeah. So then you have a, okay, your Gauss-Manin connection acts, so then your p-curvature also acts. And it turns out that these terms all have p-curvature 0. Okay. So this induces okay. So psi applied to the ice filtered piece of your conjugate filtration will land in this term. So again, I'm skipping the computations because I'm running out of time. So let me finish the talk by drawing a commutator diagram. So GRA conjugate, RA plus B push forward omega x over s maps to fs pullback s over t considered with gr on a plus 1 r a plus b high lower star x over s. There's a isomorphism from this to provenience pullback of RA pi lower star omega b x over s fs omega 1 s over t and so fs pullback R a plus 1 pi lower star omega b minus 1 x over s. Okay, so this map is inverse Cartier isomorphism up to proper identifications. Sorry, I forgot to mention that in order to have this diagram, assume that your Hodge-Rham spectral sequence degenerates, your Hodge cohomology are all locally free, blah, blah, blah. So standard package of assumptions. and then you have this. The morphism downstairs is given by taking car product with the Cordero-Spencer class. Okay, so it's not important to copy this diagram down. Let me just summarize what it does. As you know, if the Rham spectral sequence degenerates, then your Gauss-Manin connection acts on the graded pieces, and that is given by taking car product with the Cordero-Spencer class. The point of this diagram is that p-curvature applied to the graded pieces of the conjugate Hauch filtration is via the Cartier isomorphism given by taking car product with a Frobenius pullback of Cordero-Spencer. So there's an analogy with what happens for the usual Hauch filtration. All right, that concludes my talk. Thank you for Yes.
Can you just say a word about what that e to the p means inside of the nabla?
This?
Yeah. All I mean, the p power of a derivation is a derivation here.
Yeah. Oh, also, I want to get finish with a remark. As I was preparing for the talk, I noticed that you can totally define and make sense of the conjugate filtration in calculus 0 as well. And I wondered why people not talk about it. And here's my guess on why that happens. So okay. So for the usual Hauch-Rham spectral sequence, you can talk about it in calculus 0, and by spreading out, you know that generically you have a phase change. Suppose now that your conjugate Hauch filtration also can be spread out and satisfy some generic phase change. This is probably false, but let's suppose it does. Even if it does, then by the fact that your terms are computed by Cartier isomorphism, you already see that it cannot patch up nicely because Frobenius at different p will not patch up in some natural way. So either you do not commute with phase change, or even if you do, you are some very weird object. So I guess that's why people don't talk about it in calculus.
Sorry. People have studied conjugate filtration later on, but the problem is that in calculus 0, it's too hard. So like it turns out that, like, for example, it detects all the cycle theory of your variety.
Oh wow.
So it's like, for example, so if you look at this paper about this second class in physical cohomology, he makes some conjectures about the behavior of the conjugate filtration and makes a characteristic, which I'll say maybe something about tomorrow, which are like some kind of analog of the Hauch conjectures. But I mean, people absolutely have studied this stuff.
Are there any phase change properties about the conjugate filtration?
Arguably, this conjecture is some kind of phase change property. So
Okay.
you can detect one piece of the conjugate filtration if you live in character 0 by looking on p for almost all p. But beyond that, I don't know. Okay. And they're not coherent.
Okay. Oh yeah, it's so yeah, right. So in characteristic p, the terms in your conjugate filtration are known to be quasi-coherent, but in general, no, they are not known to be quasi-coherent.
Tomorrow we start at 9.
Tomorrow